Okay, so let's have a look at how mechanical advantage and speed ratio can help you figure out the efficiency of a machine. So we've talked before that mechanical advantage is a comparison of the forces, force output over force input, that go into using a machine. The input by the person, the output by the machine itself. And we're also looking at distances where you've got the input distance compared to the output distance. The ratios really should come out to the same number. So in a perfect world without friction at all, the number of times that the person has to move further than the load should equal the amount of effort that the machine is multiplying on their behalf. Okay, so like I say, in a perfect world, an ideal world, that's a world without friction. Okay, now because we are bound to our wonderful Mother Earth, there is friction that we always have to overcome. Now, friction is a force that opposes motion. Okay, there's friction in every machine that we use, and friction, basically anything that has moving parts is going to create friction. Of all the energy that the person puts into that device, some of that will be converted to friction-created heat, friction-created sound. What if sparks were given off? That would be another place that energy could go. And all of those things would be considered to be wasted forms of energy, not useful. Okay, so a machine heating up, unless it's meant to do that, is actually a machine's sign of being inefficient. So we can look at the amount that the person moves, the distance, okay, the speed ratio right here, and we can compare the number of times that we actually see that machine multiplying the force. Because in every device, when it has friction, the person operating the device is going to have to give just a little bit more input force to overcome the friction. Okay, so that is the spot right there where friction affects that force relationship. And if you make the force input a little bit higher, well, look, mathematically, that's going to come out to a bit lower number. So what we see in reality is that the mechanical advantage never quite equals the speed ratio. It's always somewhere less. And the further less, or the further behind that mechanical advantage is, the less efficient the machine is. I've always compared it to students calculating their percent on a test. You want to see what you got compared to the maximum amount of marks, and then we use a little equation to calculate the percentage. And we use that very similar equation right here to calculate a machine's efficiency. So when we do efficiency this way, we're going to take the mechanical advantage, which is like the force performance that machine is able to generate. And we're going to divide it by the maximum amount that it should be able to generate, if not for friction, and that would be the speed ratio. And then to get a percentage, we'll multiply it by 100. Okay, so this is the formula. It's one of the formulas for efficiency that you've used this section, and we'll talk about the other one later when we learn a bit more about work. All right, so let's do a sample calculation. With this, if you look and we're comparing force input, force output, distance input, and distance output, that means that in order to calculate the efficiency, you may need to solve mechanical advantage and then speed ratio first. So this could mean a 3-step calculation. If you need those two values first, then you're going to be calculating them from the two forces, the two distances that are given in the problem, and then take those answers and put them into your efficiency calculation. Okay, so let's see how this looks. All right, Janine was moving a couch onto the back of her truck. She used a ramp. Okay, so a ramp is important information. Now, the ramp was 4 meters long. Whoops. I'm going to draw this. We've got a ramp which looks like a triangle. It was 4 meters long. That's this distance here. And it was 1 meter off the ground. Okay, now these two distances, the person always walks up the ramp. So that makes 4 meters our input distance. And in the end, the couch, ends up moving 1 meter from the ground to a height of 1. So that ends up being our output force, output distance. Okay, now forces. Janine applies a force of 100 newtons. Because Janine applied it, that will be our force input to the couch in order to move it up the ramp. The couch itself has a weight of 350. All right, and that is the load. So that will be our force output. Okay, so we've got a lot of numbers figured out now, and now we just plug them into our formulas. Okay, so the mechanical advantage is MA pho over phi. Next step is to substitute. Force output was 350 newtons. Input was 100 newtons. All right, so that is going to come out to 3.5. No units, they canceled out. All right, speed ratio. Die over dou this time. That was 4 meters input over 1 meter output, which gives us a speed ratio of 4. So we've got our MA, we've got our speed ratio, and now we can calculate efficiency. So efficiency is going to take the mechanical advantage and just divide it by speed ratio and multiply by 100. So we'll go 3.5 divided by 4, which gives us, or multiplied by 100, which gives us 87 and a half. Now the unit for this will be percent. So it's kind of like saying you scored 87.5% on a test. Sounds not too bad. Okay, so practice, you've got lots of things you can practice with, but yeah, efficiency is a 3-step question typically. All right, have fun with that.